Welcome to the course on Python for data analytics, machine learning and generative AI. In this session, we will focus on statistics, which forms the backbone of data science and machine learning. By the end of this session, you should be comfortable applying statistical concepts using Python and interpreting results correctly.
Probability helps us measure how likely an event is from 0 to 1. A probability distribution is a mathematical function that describes the probability of different possible values of a variable. The probability distribution tells you how the probability is distributed across all possible values of x. In data science, distributions explain how a random variable behaves. Once we understand the distribution, we can make better predictions and inferences. In this session, we will explore key distributions and how to implement them in Python. Let us begin by importing the libraries. We import NumPy for numerical operations. We import Matplotlib for plotting graphs. We import ipystats to work with probability distributions. We also import pandas, which is commonly used for data handling. Next, we set a random seed. This ensures that the seed numbers generated are the same every time we run the code. It helps in learning and comparison. Before learning distributions, we must separate variables into discrete and continuous type. Discrete random variables take countable values like 0, 1, 2 or 3. These are described using a probability mass function or PMF. Continuous variables takes infinite values in a range like height or time. Bernoulli and binomial distributions model success and failure outcomes. Bernoulli represents one trial like a single coin flip. Bernoulli represents one trial like a single coin flip. Binomial represents multiple independent trials like 10 coins flip. In Python, we use ipystats binom to generate binomial random values. These are widely used in calculations, A/B testing, and quality control. The Bernoulli distribution is the simplest distribution. It has only two outcomes. For example, yes or no, success or failure, click or no click. Here we set the probability of success is 0.6. Using the Bernoulli random variable function, we generate 1000 observations. Then we plot a histogram. You will see two bars, one for 0 and one for 1. This shows how often success and failure occurs. Binomial distribution extends Bernoulli. Instead of one trial, we now have multiple trials. For example, number of defective items in a batch, number of heads in 10 coin tosses. Here, the n is equal to 10 trials. Probability of success is p is equal to 0.5. We generate 1000 values and plot the histogram. Each bar shows how many times we got 0 successes, 1 success, 2 successes, and so on. The Poisson distribution models how often events occur in a fixed interval. It is a discrete distribution used for counts like calls per hour or arrivals per minute. It depends mainly on one parameter, the average event rate, often written as mu. In Python, we generate Poisson samples using scipy.stats.poisson. This is extremely useful in queuing, network traffic, and event prediction. The Poisson distribution models events occurring over time or space. For example, number of calls per hour, number of customers arriving per day. Here, lambda is equal to 3, which means average 3 events per interval. The histogram shows how frequently different counts occur. This distribution is very common in operations and service systems. Geometric distribution answers a different question. It tells us how many trials are needed until the first success, how many visits before the first purchase, and how many calls before the first sales. Here, the probability of success is 0.3. The histogram shows that smaller values occurs more often, which means success usually happens early. Continuous distribution deals with measured values and not counts. The normal distribution is one of the most important models in statistics and inference. It is continuous, symmetric, and bell-shaped, defined by mean and standard deviation. Many natural and measurement-based phenomena follow a normal pattern. In Python, we generate normal samples using scipystats.norm. This distribution is also a foundation for hypothesis testing and confidence intervals. The normal distribution is also called the bell curve. It appears everywhere, like heights, measurement errors, exam scores. We generate data with mean is equal to 0 and standard deviation is equal to 1. Instead of a histogram, we plot the probability density function. The curve is symmetric and centered at the mean. Exponential and gamma distributions are used to model waiting time and reliability. The exponential distribution describes time between events in a Poisson process. It is famous for being memoryless, which means the past does not affect the future. Gamma is a generalization of exponential and models accumulated waiting times. In Python, we use scipystats.expon and scipystats.gamma for implementation. The exponential distribution models waiting time. Example, waiting time in a queue, time between arrivals. Here we generate waiting times using a scale of 1. The histogram shows many small values and fewer large values. This tells us that short waits are more common. Gamma distribution is more flexible. It is used in insurance claim, rainfall modeling, risk analysis. Here we use shape and scale parameters. The histogram shows the right skew distribution, which means more small values and fewer large ones. The uniform distribution represents the idea that all outcomes are equally likely. It is a continuous distribution where every interval of equal width has the same probability in Python. We can generate uniform random values using scipystats.uniform. This is useful for simulations, sampling, and baseline random modeling. Visually, the uniform distribution looks flat because probability is evenly spread. In the uniform distribution, all values are equally likely. Random sampling and simulation models are examples of uniform distribution. We generate 1000 random values between 0 and 1. The histogram looks flat, showing no preference for any value. The log normal distribution is useful when values cannot be negative. Data grows multiplicatively. Examples are income and stock prices. The histogram shows strong right skewness, and this matches many real economic data sets. Now let us fit a distribution of data. Now let us fit a distribution to data. We first create a data set that follows a normal pattern. Then we estimate the mean and standard deviation from the data. This step is called parameter estimation. Next, we plot the actual data histogram, the fitted normal curve. If the curve matches the histogram well, the distribution is a good fit. This technique is widely used in data analysis and modeling. Let us apply distributions to small real-world problems. We can use the Poisson distribution to model daily demand. We generate demand for 30 days. Then we calculate the average demand. This approach is common in inventory planning. We use the exponential distribution to simulate hospital waiting times. The average waiting time gives insight into service efficiency. We also approximate daily stock returns using normal distribution. We generate 252 values representing one trading year. The mean return helps in financial decision making. Finally, we perform a Monte Carlo simulation. Monte Carlo method uses random sampling to estimate probabilities. Here, revenue follows a normal distribution, cost also follows a normal distribution. Profit is calculated as revenue minus cost. We then calculate how often profit is greater than 0. This gives the probability of making a profit. Such simulations are widely used in finance, risk analysis, and business planning. So let's summarize. In this session, you learned different probability distributions, their real-world meaning, and how to generate and visualize them using Python.
Thank you.